Good morning. I don't want to be the first one to get shot with a Nerf gun, so I'll dive right into this. Sometime last year, in June last year, Kaspersky researchers started publishing some details about the campaign they uncovered. They dubbed it Operation Triangulation, and it was a pretty involved campaign of exploits against iOS devices. The target in this case was them, Kaspersky researchers. They got wind of this campaign against them because repeated reinfections of devices were required by the threat actors in this case, and they noticed some suspicious egress connectivity. They set up some traps to catch the samples and reported them to Apple, started publishing afterwards, and we got wind of some of the details about the Operation Triangulation. This resulted in a bunch of bugs getting published and patched. There's a bunch of CVEs assigned to them. Most of them have been analyzed in the public. The attack chain, the complete attack chain, bug chain for this exploitation campaign was pretty involved. There were many, many steps in it, many exploits used to achieve the goal. And most of these have been talked about and analyzed by the public, and there's proof of concepts available for them, especially the ones, the more juicier ones, like the PLL bypass that relies on MMIO issues. There were some fun exploits to be analyzed in there. Kaspersky researchers did their presentation at Chaos Communication Congress last year that goes deeper into the details of what they have uncovered. There is one thing that hasn't received much public attention, and that is the initial attack vector, or the initial vulnerability that was exploited. This was reportedly a font vulnerability or a vulnerability exploited through a malicious font that was embedded inside a PDF document. This, and only this, is what I'll be covering today, recovering and uncovering some of the details of the vulnerability itself. A little bit of motivation on why I'm interested in this. I work as a vulnerability researcher at Talos, Cisco Talos, where we do third-party vulnerability research. We find vulnerabilities in popular software that is used by public at large and our clients. We analyze those vulnerabilities, write advisories, and notify the vendors so the vulnerabilities can get patched. We're always keeping pace with current developments, and looking into currently exploited vulnerabilities is one of our main topics. Me personally, over the last 5 or so years, I've reported several dozen vulnerabilities in PDF readers, like Adobe Acrobat, Foxit PDF, Chrome's PDF reader. So PDF exploits and PDF vulnerabilities are of special interest to us. You can find more details about this on our website, where we published our advisories and vulnerability reports. Why do we care about this particular vulnerability since it's already been patched? In short, that is our day job. By understanding these vulnerabilities that are being exploited in the wild, we can make sure that we are on the right track when trying to find additional vulnerabilities, that we're focused on the right things. And by analyzing these vulnerabilities, we can kind of learn a lot. There were a couple of similar in nature, not in bug class, vulnerabilities published in the last couple of years targeting iOS devices and different high-profile targets. And all of these have a couple of things in common. One of them is that they're very, very complex beasts when it comes to exploitation. In the case of forced entry vulnerability that was present in the JBig parser, the exploit for the vulnerability is practically a virtual machine built around the vulnerability itself to achieve better primitives for exploitation. In case of BlastPass, we saw a very intricate manipulation of the file format for WebP to be able to exploit this. And if you remember last year's Ian Beer's presentation about dissecting some of the sandbox escapes that they uncovered, that ridiculous-looking NS expression exploitation framework with he had an image that looked like Eye of Sauron or something. We don't have the sample for this particular vulnerability that I'm talking about today, but I would expect something of similar complexity to be packaged inside it. Another motivation for dissecting these vulnerabilities is to potentially come up with the detection methods, signatures that we could apply to various places to potentially catch samples in the wild. Since the vulnerability is public, chances are someone else is gonna look into it and try and abuse it, which didn't really happen in this case, but it can happen in general. I would like to mention Matt Sweesh's elegant bouncer tool. He tries to make algorithmic detection of samples for these high-profile vulnerabilities. He has entries there for forced entry and blast door. He added one for triangulation. However, digging into it, it's, the algorithm that it uses is pretty naive, makes some assumptions that result in a large number of false positives. So it's not really useful to apply on a large corpus of samples. We need to really understand the vulnerability and what it's about to be able to properly detect a malicious sample. This is obviously a high-impact vulnerability. It's all of these kind of are in the zero-click or one-click attack surface. Fonts themselves are a pretty important attack surface on all platforms. So performing or understanding the vulnerability could lead to some additional interesting work. That is, variant analysis is always important in analyzing these vulnerabilities. If there's one vulnerability, chances are there's some similar issues in the code base. So by understanding the vulnerability, we could perform variant analysis as well. I already mentioned catching samples, and ultimately understanding how these vulnerabilities are exploited can, again, lead to additional insights for how to proceed with additional work. Let's go over what we know about this particular vulnerability. The biggest problem here, and why I'm here talking about this today, is that nobody would actually share a sample of the malicious or of the malware sample with me of the actual exploit. There's probably a very good reason for it, but we know very little about the vulnerability, and we have to keep digging into it to reconstruct it ourselves. What we know about this CVE-2023-41990 is that it was exploiting a vulnerability in the TrueType font renderer on macOS. It was delivered inside a PDF. PDFs can have embedded fonts in them. It was somehow abusing an undocumented instruction in the bytecode interpreter for TrueType fonts. And that is basically all that's published by Kaspersky researchers. So bytecode interpreters might sound weird if you've never worked with fonts before, especially font vulnerabilities. Like, why is there an interpreter in fonts? So to kind of understand that, we need a bit of history first. In the beginning, fonts were bitmap files or bitmap fonts. Those don't scale well. They always look blocky. Yeah, you can imagine not being able to increase the font size or not change them into italics or something like that. They're not very easy to use. Sometimes in mid-'80s, Adobe developed their proprietary technology based on PostScript language. So it was the first kind of implementation of the outline fonts, meaning scalable fonts. It was very verbose. Each font was implemented in a couple of files and so on. Similarly, Apple developed their TrueType font technology, which is also outline fonts, hinted fonts. We'll come to that a bit later. And this was kind of in use on their system in the early 90s. This is a very, very high-level overview of the history of it. And sometimes in the late 90s, Microsoft and Adobe wanted to beat Apple at this, so they joined forces and came up with something called OpenType, or compact font format, which is based on PostScript fonts from Adobe, but in a binary representation. It's similarly outline fonts, and so on. If you kind of think about how fonts are used, they're very, very performance crucial, rendering every glyph on the screen. If it doesn't have high performance to do that, everything gets slowed down. So it's very important for the rendering to be fast. On the other hand, they're very complex if you think about what fonts support, and combination of those two things, performance and complexity, doesn't bode well for security. Famously, Windows used to do font rendering in the kernel, so you can have direct from the browser access to the kernel primitives, and that was a very interesting exploitation area. Additionally, the bytecode or the char strings I mentioned before make for some beautiful exploitation primitives for shaping the memory layout and so on. The important bit about fonts is that they're reachable from anywhere. Every single web page that your browser visits can embed a special previously unknown font in it that your computer will happily interpret and display. So this has been a source of vulnerabilities throughout the years. I'd be remiss not to mention, and for much more detailed introduction to font vulnerabilities, Juru's work, they dubbed broken type. They've spent a couple of years basically dissecting the font renderers on all platforms, fuzzing them, auditing them manually, performing really, really extensive research, and there's a couple of blog posts about it, a couple of presentations that go really deep into the history of fonts themselves, the inner workings of font renderers, and the vulnerabilities that were present. So thanks to them for clarifying a bunch of stuff while I was working on researching this particular vulnerability. Just a little bit more history on the font file formats. Today, if you take a look at any given font, chances are they're going to internally look pretty much the same, no matter if it's a TrueType font, an OpenType font, or an older bitmap font of some sort. They're all based around this file format called SFNT, which is a container format based around tables. In SFNT, there's a table for everything. There's cross-references all over the place. Ange Albertini's excellent file format dissection graphs like this can help understand how it works, but it's pretty complex. So in this case, both OpenType fonts and TrueType fonts kind of look indistinguishable from just looking at the file. You kind of have to dig into the structure a bit more to understand which one's which. A small aside, since fuzzing is important for vulnerability discovery, font fuzzing and fuzzing SFNT or TrueType or OpenType fonts is probably the worst case for mutational coverage-guided fuzzing because the file format is so fuzzing, so malicious towards fuzzing, I guess. There's cross-references all over the place. One table has offset references into another table. It has offset references into another table that looks up things in yet another one. So changing a single byte inside a file tends to render the whole file unusable and unparsable. So fuzzers are not going to get far. Dumb fuzzers are not going to get far. You need structure-aware fuzzing if you're trying to get any useful results out of this. But to get back to the topic today, I mentioned something about an interpreter, and to understand that, we need a slightly bit more of history. All of those outline fonts, both TrueType fonts and OpenType fonts, are so-called hinted fonts or instructed fonts. And what that means is that the font itself can kind of tell on what sort of display it's being displayed and at what point size. So it can hint the renderer on how it wants the pixels to be arranged. If you look at these images, you can see that the one on the right looks much better than the one on the left, and that's the difference between hinted and unhinted font. Hinted means it'll tell the renderer, hey, shift this bit to the left or to the right so it looks better on the screen. And to do this, fonts have bytecode inside of them that basically describes the calculations on how to place those pixels when rendering them. Obviously, this can be pretty complex and is basically what we're digging into today. So TrueType font has an interpreter, or TrueType font renderers have interpreters. Every TrueType font has bytecode built into it that executes at different levels for different purposes. The TrueType font interpreter is a simple stack VM. It basically, if you disassemble it, it looks like it pushes a couple of bytes onto the stack, then calls an instruction that consumes those bytes, makes some transformation, and pushes results onto the stack, and so on. There are a couple of dozen instructions that do all sorts of things related to pixel placement, and these manipulate, on the logic level, they manipulate glyph data, points, curves, lines, and symbols like that. But on the more practical side of things, how this boils down to in memory, these manipulate pointers, indices, and structures, arrays, they iterate over memory, and have a chance to mess things up and result in memory corruption issues. So, TrueType fonts were developed by Apple. This is an excerpt of most of the instructions built in the TrueType font interpreter. In Apple's implementation, all the instructions are implemented as separate functions, so the interpreter just goes down the bytecode and calls the appropriate instructions for each opcode that it sees. If you spend some time digging through other code bases or take a look at the leaked sources out there online, you would see that Microsoft has very similar implementation, and this is because Microsoft directly licensed this technology from Apple back in the day when they were developing their own, and then modified it and made it suitable for use on Windows. So this can be a helpful thing when reverse engineering these renderers. Similarly enough, and kind of in an interesting twist of events, others borrowed from Apple as well. Nintendo at some point licensed the technology from Apple. This got leaked. This is a Super Mario game leak from 1994 that has the same font manager inside it. And the structure is pretty closely mapped to what's used inside of macOS's font renderer today. So this is a good starting point for reverse engineering. But back to the vulnerability. Now we have the background to understand why there's an interpreter and why there could be vulnerabilities in fonts. Let's dig into what we know so far about the vulnerability. From Kaspersky, we know that the vulnerability was in this undocumented Apple-specific instruction called adjust. There's only 1 or 2 mentions of this online. It has 2 opcodes for this instruction, but no one ever documented why it's there or what it does. There's some speculation in free type library about what it does, but no font in the last 3 decades has actually used this. It's just remnant in the code. Digging into the code of the libfont renderer, the font renderer on macOS, this instruction isn't really hidden. Even if it's undocumented, the code is there. The font renderer has partial symbols, so you can easily find it. We just don't know what it does, basically. Looking at the code, looking at the control flow graph, it kind of looks a little bit complex, but not too bad. There's a bunch of error checking that errors out. As far as vulnerabilities goes, I'll call your attention to one big loop that goes around the whole block of code, and then 2 smaller loops at the end. Loops in code mean complexity, means traversing an array or something like that, and this is probably where we're going to be looking for finding the vulnerability. Small side note, usually when doing this sort of end-day root cause analysis, when trying to figure out the vulnerability that's been patched by the vendor, we perform patch analysis or patch diffing. This was not useful in this case because Apple patched this by simply removing the whole instruction from the code, so there's nothing to diff against. We already know the vulnerability is somewhere in this function. We don't know exactly where. But yeah, they removed it so we can do patch diff, and we'll have to do things manually. First things, what we wanted to do is find a starting point, a test case, a font file that hopefully uses this instruction, so we could see how it was used originally, what its intended purpose is. So what they did was gather all the fonts that they could find from all the online repositories, made a corpus of fonts, disassembled them all using a Python package called font tools, which is excellent for doing any sort of font manipulation. It has so many built-in functionality that makes things easier if you want to modify these SFNT fonts. We were hoping to disassemble a font, find one that used this undocumented instruction, and then use that one as a starting point for further reverse engineering. But we had no such luck. We couldn't find a sample that readily used it. I probably didn't dig too far back into the past to find one. So we have to reconstruct this manually. And the idea here is that I'll take a sample font that has some bytecode in it. I'll modify to insert this undocumented instruction, run it in a debugger, and get to see the code executed and then figure things out. The entry point to the bytecode interpreter on macOS is this function called fnt execute, which, as I mentioned earlier, takes an opcode, calls a associated function to it, and goes down the bytecode, executing it as it comes. So the idea is we start up a program that parses fonts, in this case parses PDFs. We set a breakpoint on that font execute function, run the program, and nothing happens. The program runs, but the breakpoint isn't hit. So what's the actual problem? It seems like we can't hit the interpreter, and there must be a reason why. It doesn't make a whole lot of sense. Like, the code is there, we're just not hitting it for some reason. Well, there is a reason for it, and there's a bit of a roundabout way of going about it. There's this thing called auto-hinting. If you recall, when I started talking about hinting and hinted fonts, I mentioned low DPI displays, meaning hinting was very, very important when the displays we were using were very low resolution. Today, all of our displays, especially on macOS and iOS devices, are very, very high resolution, high DPI, so the hinting doesn't really come into play all that much. And the OS itself is much more, the hardware is more powerful, so it can do much heavier analysis on how to render the fonts. So it does run some heuristics to display fonts rather than using the interpreter. It can do better than the font itself can. And this is called auto-hinting. On Windows has a technology called ClearType. Which is basically this. There were a couple of online sources that say macOS outright ignores the interpreter or ignores hinting. I couldn't find an actual source claim for that, but it boils down to the fact that if you want to render fonts as fast as possible, you want to avoid invoking the interpreter as much as you can, because that's a slow path. Your heuristic might be faster. But, So the interpreter is obviously not completely ignored, otherwise the vulnerability wouldn't be triggerable and the exploit wouldn't work. So there's gotta be some way to actually trigger it, some way to trigger the slow path and go down force the renderer to interpret the font. And if we take a look at the code itself, there's a couple of entry points to running the font programs or bytecode interpreter. One is to run font program, which runs at the beginning of the rendering of the using of the font. There's a pre-program and a glyph program, which runs for every glyph that's being rendered. In all of these cases, there's a couple of guards, if blocks, before entering this part of the code that kind of make it take the faster path and not actually invoke the interpreter. So in all these cases, we have to do some reverse engineering to figure out what the right conditions are to trigger the slow path and invoke the interpreter. Most of this work was about reverse engineering, but I don't know a good and interesting way to talk about the reverse engineering steps, so I'm just going to give you the results. it turns out that if you set these two properties in a font, the high units per M is the base unit size in fonts. If you specify high units per M and high lowest recommended pixels per M, this tricks the font renderer to believe that this particular font is complex enough that it needs the interpreter to run. And so, if we patched our fonts to have these properties are just in a table. You don't have to dig too far into the font structure to modify them. We can just apply them on all the fonts we have to make sure the interpreter runs. Once we do that, once we change the font, go back to the debugger, run it, and indeed we can actually trigger the interpreter. We can see the call stack here goes through creating a glyph element and then run font program, font execute, and then finally fnt fdef, which is fdef is an instruction in the bytecode interpreter. So with this, we can actually get to the interpreter to execute it. Again, a small aside, if you were fuzzing fonts and hoping to find interpreter vulnerabilities but weren't paying attention to the code that's actually being executed, you could easily miss that none of the fuzzing actually hits the interpreter because it's using auto-hinting and not the interpreter. So again, doing some reverse engineering with fuzzing is crucial for good results. Before we go further into details, there was a couple of interesting facts that I uncovered while digging into this. PDFKit and core text are the frameworks on macOS that implement PDF parsing and rendering. PDFs themselves can have all sorts of fonts embedded inside of them. There's type 1 fonts, type 3 fonts, PostScript fonts, TrueType fonts, OpenType fonts. It's a complicated mess, but you can embed fonts inside of PDFs. Not all of the file formats, but more common ones. There's a subset of font formats that PDF specs themselves supports. However, while digging through this, I uncovered that PDFKit and core text don't really care about what font you specified in the PDF. They'll take the font from the PDF, and then the font renderer will actually decide which font type this is. So you can trick the renderer into rendering fonts that the PDF spec doesn't support in general. So you can shove WAF2 fonts inside a PDF, which generally shouldn't work, but on macOS it does because the font renderer will actually run the font. This also means you can use ancient fonts, like Macintosh fonts called D fonts. It's interesting, again, that the macOS by default won't preview these fonts, but it will happily render them if they're built into a PDF. So you can trigger some really, really ancient code paths in this PDF renderer just by forcing or ignoring specifying the correct file type inside a PDF. And yeah, as I mentioned, it was interesting to dig into that support for ancient font formats like bitmap fonts and D fonts, which are all Macintosh fonts. They're still supported on macOS today. If I had infinite time, I would keep digging down this path because there might be something curious in this code base. But kind of to get back on the vulnerability, on the topic at hand. So at this point, we can reach the interpreter, and we can probably reach the vulnerable instruction. We can use that font tools Python package to inject. Font tools Python package lets you decompile a font into an XML file, then modify it manually, insert instructions, modify other properties of the font, and then recompile that XML back into an SFNT binary font. Font Tools doesn't have support for this undocumented instruction, obviously, but it lets you specify arbitrary opcodes by just saying instruction and then the number of the byte of the opcode. And 144 is an opcode for a just instruction. So we can insert this undocumented instruction into a font, run the debugger, and see if we can catch it executing. And indeed, in the debugger, we can. set a breakpoint on that, and hit it while executing. So we can now keep digging into the function to see what it does. There's a lot of unknowns that we need to solve if we were to recover or reconstruct the vulnerability here. The first one is what the instruction does logically. The second one is how many parameters it has, because if we're just inserting instruction at random, it's just going to error out early, and we're not going to reach any interesting code inside of the function. And for it to do anything interesting, we need to provide it with plausible parameters on the stack. And finally, what are the preconditions for the vulnerability to trigger? To understand what the function does, we kind of go back to how fonts work. Outline fonts work by specifying contours or curves. Each glyph that gets rendered on the screen is specified by one or more contours, which describe the font. And these contours consist of points, or contours are Bezier curves, and Bezier curves are defined by a couple of points in the coordinate system that define that curve. And what that hinting stuff does is basically manipulating the position of these points so the glyph gets rendered better. An interesting observation about these points, how they're represented in several layers of kind of working with fonts, is that the logical representation is that the curve is specified by an XY point, or several XY points somehow. It's a Bezier curve. And there's an array of those XY points that specify a curve. To be more optimized for file storage, I guess, for writing down in a binary file format, in the SFNT format, these points are all points of the glyph, or all curves of the glyph, sorry, all points of all curves of the glyph are stored in a single array, and then there's also an array of endpoints for those contours. So all the points are in a single array, and then there's an array with endpoints. So if you know where one curve ends, and you know where the next one begins, and so on. It's a little optimization to have the binary representation be more compact. But on the third side, since the renderer needs this to be rendered to be performant, it keeps things differently in memory. So there's a couple of different structures. There's a couple of different arrays. One is like the hinted outline array that contains all the points, but then there's an array of start points and a separate array of endpoints. All of these contain indices into each other, basically, and have to be synchronized at all times, otherwise memory corruption happens. So if we can find a way to manipulate these indices and these arrays to desynchronize them, things start to break, and we can find vulnerabilities. And these have been source of vulnerabilities in the past. So what the function does on the high level, it doesn't really matter for us. We're working on trying to find a vulnerability here, so we don't really care about the logical or semantic effect of the function. But it finds a specified curve as a parameter, it iterates over its points and moves it to the left, to the right, up or down. It basically adjusts that curve that we specified somehow. The second question, how many parameters it takes, is important, and from reverse engineering it, after you figure out the functions and the layouts and some of the structures, it becomes pretty obvious that it takes 3 parameters. The first parameter is an index into a control value table. This is a large table with a bunch of values in it. The second one is the contour point index, and the third one is the same. It just depends on the rest of the code which one gets used. The contour point index is what specifies which contour this adjust function will be applied to. What it really does is what we're interested in, what it does in memory, or how it achieves its goal. To translate this into memory manipulation, it indexes into a memory buffer, it iterates over the elements in the memory buffer, and changes the value of those elements of the memory buffer, of that array in memory. What we're interested here is if we can somehow get it to do something wrong while iterating through that memory array, we can maybe achieve memory corruption. So here's the interesting code paths and some pseudocode of what the function does. Just recalling back to those two loops that I pointed out, it turns out that the code will very loosely, it finds the curve that it needs to operate on by iterating through all the points, and then proceeds to update the values. It first does it from the target point going up, and then changing the direction starting from the start. And then, again, starting from the same point, going down and wrapping back. Again, we don't care why it does this. It's important that, that this is what happens. So is there a path to memory corruption here? Can we get that index into the array buffer to point outside of the array and start overwriting the adjacent memory? This is one of the important while loops, and if we can get this index value to point outside of the array, we have memory corruption. How to get it to point outside of the memory array is the next question. At this point, we control a number of things. Just because we're supplying the whole font file, we control the number of points directly in each glyph and in how many glyphs there are. We control the number of contours. These all feed into the kind of execution of the function. We can control which contour is the target one to manipulate, the first one, the last one, the one in the middle, and so on. We control the target point inside of the contour, so we can precisely control where the manipulation starts, and we basically control the size of the buffer that's allocated for all of these points, because it's based on max points count, which is specified in a header table somewhere, and some other stuff. So we have all of this to control the execution of the function. There's an important bit when you start going down the code of the function, and that is that while it's trying to find the target contour, it'll iterate from the points from the back going down, but it never checks if the initial guess is outside of bounds. If the initial check is bigger than the first or the last point in the contour. So index can point outside of the array of points to begin with, even if the start and finish points are smaller. And this, if we can manipulate the memory adjacent to it, we have our vulnerability right here. So is it that simple? Is it just like out of bounds memory write and we get to control everything? Well, it's not really, because there are a lot of constraints that limit the sizes of these index values, the out of bounds accesses. It's very important to control what's after in the memory, and reconstructing this from scratch is kind of we have limitless possibilities to control the layout of the memory because we have that bytecode interpreter, but it can be difficult to foresee what's the most exploitable path. And then we have the question of controlling the value that's written, because that changes the values of the points just a little bit. I think it's a bit exactly, so adjusting them is, we don't have full control over the overwrite. At this point, I can only speculate about the exploitation, given that the vulnerability is not really that amazingly easy to exploit. I would, again, expect the actual exploit to be very complex, based around this small primitive, to build it into something larger and more complex. And just to conclude with a couple of things, we did perform variant analysis because we, at this point, understand the vulnerability. We could search for similar issues in the adjacent code in other instructions. There are a couple of other undocumented instructions as well. Can we make a signature for the exploit? We can, yes, but it requires really dissecting the font file format, and that will slow things down and not be really scalable. I've already talked about some fuzzing takeaways and how you would do proper fuzzing with understanding this vulnerability. One of the main questions is why didn't fuzzing catch this in the first place? Well, I already mentioned it, that the font file format is unfriendly, and there are a lot of preconditions to actually hit this vulnerability. You need to really know kind of what's going on to direct your fuzzer. And then, yeah, of course, a fuzzer can find it if you already know that the vulnerability is there. But there's some other interesting takeaways, like in this case, we needed to recover the details of the vulnerability without patch diffing. Reconstructing it from without the sample bottom-up analysis made this more difficult. If we were doing this from an initial vulnerability research perspective, we would have done things differently. There are some references to go through that were very useful when digging through this and trying to piece all the puzzle pieces together that you can take a look at. And with that, I would like to close everything, and thank you for listening. And if somebody does have a sample of this particular exploit, I won't tell anyone if it share it with me. So thank you, everybody.